Okay, so today we'll try to do some numericals on thermal properties of matter. Okay, so thermal properties of matter, it includes so many things. Okay, so in your 12th or 11th or 12th, it broadly these are the things which comes under thermal properties of matter. Okay, so one is like the difference between heat and temperature. Okay, and then temperature measurement. Okay, different scales for measuring the temperature, like degree centigrade, degree Kelvin, or so, and Fahrenheit and all. How is the what is the relationship between the different temperature scales? How to convert Fahrenheit into centigrade or centigrade into Kelvin, which is the absolute temperature that we call. So that is about temperature measurement. Okay. Then thermal expansion. Okay. Suppose if you are heating some metallic rod, how it depends on the coefficient of thermal expansion. What will be, how much will be the elongation and all that. Okay. That is thermal expansion. And then specific heat. Okay. Um, the specific heat is a property of a material, like that we'll discuss, like the amount of heat required to raise the temperature of unit mass by unit degree, like unit temperature or unit mass. Okay, amount of heat required, that will cover. Then calorimetry, which is like different concept on latent heat, specific heat, and all that. Then what is latent heat? Latent heat of vaporization, latent heat of fusion, and all that. Okay. So and then heat transfer. Okay. So heat transfer is just a part of thermal properties of matter. So when the heat is getting transferred, like say you have a iron rod, you are hitting it at one end. So the transfer of heat from one part of a body to another part, that is called conduction. Okay. Similarly, you have convection also, and you have radiation. So conduction and convection, they need a medium for transfer of heat. Okay, suppose you are heating some water by keep putting it in a vessel, that is natural convection. Okay, so there is something called forced convection also. Suppose you are sending pressurized fluid. Okay, so when you are pumping some hot fluid, the mode of transfer of heat from that hot fluid to the surrounding, that will be called forced convection. Even your blood circulation. So your heart is a pump, and the blood is being uh, pressurized blood is being circulated throughout your circulatory system. That is also example of a forced convection. Okay, and then there is radiation. Okay, when two bodies are separated, it does not need any medium. Through vacuum also the heat can get transferred. So for example, absorption, the heat is coming from the sun to the earth, so there is no need of any medium. It's a electromagnetic wave, and radiation is transfer of heat without any medium. So there are three modes of heat transfer: conduction, convection, and radiation. Okay. So broadly these are the things. So uh, I'll put put the major driving formulas which will help you to solve the numericals. Okay. So take a picture of this. Okay, so I think I have.
એના
Huh?
ફોર્મ્યુલા કરીશું ક્વેશ્ચન્સ કરના એ ચેપ્ટર.
Okay, so we'll just have a recap in 10 minutes. Okay, we have done, but doing a recap is not a problem. Okay, so we'll just recap it. Okay, so when you start something, you have to have a recap. Okay, so Yeah. Okay, so the major driving formula is something like this. Okay, so the conversion between centigrade to Fahrenheit. Okay, so it is between the like say freezing point to the boiling point of water. So the freezing point is say 0 degree centigrade. Okay, and let us see the boiling point of water is 100 degree centigrade. Right. Right. So this is in centigrade scale. Okay. So corresponding to centigrade scale, there is this Fahrenheit scale. Okay. So in Fahrenheit scale, the freezing point is say 32 degree Fahrenheit, right? And the boiling point is 212 degree Fahrenheit. Okay. So the relationship between the Fahrenheit and the centigrade scale. So this is Fahrenheit scale. It's scale. Okay, so the relationship between Fahrenheit and degree centigrade is being written as this. So T degree centigrade minus 0 minus 100 minus 0. Okay, it is equal to temperature in degree Fahrenheit minus 32, right? Because it is starting with 32 divided by 212 minus 32. Okay, so with this we'll do one numerical which has come in your come in one of your JEE exam. Okay. Uh, yeah. Okay. So the temperature of an object is 60 degrees centigrade. Its value in Fahrenheit scale. Okay. So it is given that temperature of an object is 60 degree centigrade. Okay, 60 degree centigrade. What will be its value in Fahrenheit scale. Okay. So you replace T degree centigrade is 60 here. Okay, it will be 60 minus 0 divided by 100 minus 0 is equal to, we want to find this out, right? So it will be temperature in degree Fahrenheit minus 32 divided by 212 minus 32, right? So this becomes 60 by 100 divided by T degree Fahrenheit minus 32 divided by 180, right? That implies T degree Fahrenheit is equal to 60 by 100 into 180, right? Right, plus 32, plus 32. So it becomes 32 plus 60 into 180 by 100 is nothing but 9 by 5, right? Right. So so this is how you do it. Okay. So this becomes 32 plus this is 108, right? 12 108, which is equal to 140, right? So 140 is the answer. So if you don't want to get into these complications, just remember that T degree Fahrenheit is equal to 32, 32 plus T degree centigrade into 9 by 5. Okay. So just you have to replace that 60 here. Okay. So if you know this equation, you can find Fahrenheit to degree centigrade to Fahrenheit. Either way you can do. Okay. So this is the equation you just have to remember. T degree Fahrenheit is equal to 32 plus T degree centigrade into 9 by 5. That is the governing equation. Okay, so this is one question that has come in your JEE. Okay, so the conversion of temperature from Fahrenheit to degree centigrade to Fahrenheit. So you can see 60 degree centigrade is equal to 140 Fahrenheit. Okay. So that's why our human body temperature. It is normal temperature is 36.5 degree centigrade or whatever. The corresponding normal body temperature is 98.4 degree Fahrenheit. Okay, so degree centigrade scale is comparatively, we see the degree centigrade temperature will be comparatively lesser than Fahrenheit. If this is 36.5, that is 98.4. Okay. Okay, take a picture of it. Oh. Okay, so this is conversion between degree centigrade to Fahrenheit, and there is a conversion between degree centigrade to Kelvin. Okay, so temperature in Kelvin, temperature in Kelvin is equal to temperature in degree centigrade. Okay, plus 273. Okay, so this temperature is otherwise called as the absolute temperature. Absolute temperature. Okay, right. Uh, um, suppose the freezing point of water. Okay, your freezing point of water is 0 degree centigrade. That means it is 0 plus 273 degree Kelvin is equal to 273 degree Kelvin is the freezing point. Similarly, the boiling point of water. Boiling point of water, which is equal to 100 degree centigrade, that is equal to 100 plus 273 degree Kelvin is equal to 373 degree. So this is how you convert degree centigrade into Kelvin or Kelvin to degree centigrade. Okay. So when you want to convert Kelvin to degree centigrade, just subtract 273. And we have studied about Carnot engine and all. So Carnot engine is 1 minus T2 by T1. Okay. So you have a source and you have a sink. Okay. And you have this engine and you take some heat Q1 and you give away some heat Q2, okay, and you get some work done, right? This is what the engine is. So here the source temperature is T1, sink temperature is T2, right? So these temperature, before finding out the efficiency, you have to convert this temperature to absolute temperature in Kelvin scale. After that, you find out the efficiency. Okay. So that's about conversion from degree centigrade to Kelvin. Okay. Take a picture, we'll go to next. Okay. And yeah, so next we'll go to thermal expansion. Okay. Right? Thermal expansion. So, so let us say the original length. So let me say I have a iron rod. Okay. So I have some iron rod. Okay. So this is my iron rod, and let me say I am heating this my iron rod using some source of heat. Okay. So let me say the initial length of this iron rod is let us say L0. By hitting it, this rod will try to expand.
Yeah.
Okay. So let us say this is delta L, right? At the if you hit it, it will get expanded by a length delta L. Okay.
Yeah.
So the initial length is equal to L0, final length is equal to, let us say, L. Okay. So L0 is L is equal to L0 plus delta L, right? So this delta L is your change in length. Okay. So the delta L is this delta L is a alpha original length L0 into delta T.
Coefficient.
So this change in length depends on a coefficient of thermal expansion, the original length, and rise in temperature. Okay. So three things it is depending on. So more, if the initial length is more, it will expand more. If you rise the temperature by a higher value, it will expand more. So this term, this value alpha, this is called
Constant.
coefficient of thermal expansion. Okay. So the alpha is equal to coefficient of thermal expansion. Okay. So your alpha is called coefficient of thermal expansion. Okay. So this is for a 1D. Okay. So this is linear. Okay. So this is a rod only. So linear coefficient. Okay. This is linear coefficient. Okay. So you can have a rod. You can have some area. You can have some volume also, like that. So let us say this is like this. This is a rod. Let us say this is like this. This is the area.
Yeah.
Okay. Let us say this is something like this.
3D.
Yeah, it can be a 3D. Okay.
Solid.
So it is a solid. So every time you can heat it and you can find out the change in volume, change in area, and all those stuffs, right?
Yeah.
Okay. So this coefficient of thermal expansion, this can be written as alpha is equal to delta L divided by L0 delta T, right?
Yeah.
So this is called coefficient of linear expansion. And if somebody asks you the unit is important here. So you know change in length by original length. That means length cancels. So the unit of alpha is Kelvin inverse. Just Kelvin inverse. Okay. And similarly now we have discussed about linear. Okay. Similarly your coefficient of area expansion. Okay. So it will be same. Like say we write it as beta, right? Area is beta if you write. So beta is equal to, instead of length you write it as delta A
Area.
divided by A0 into delta T. This is your beta. So this is corresponding to area, coefficient of area expansion.
And volume.
Area expansion. Okay, so similarly there is something called gamma, which is delta V by V0 into
delta T.
So this is
Volume
coefficient of volume expansion. So these three things, and there is a relationship between these three. So alpha linear is half of beta is 1/3 of gamma. Just remember this. So linear coefficient of linear expansion is half of coefficient of area expansion, and it is 1/3 of coefficient of volume expansion. This is just you know that area is length into breadth. That's why. And volume is length into breadth into height. So this is just a thumb rule, you just remember. There can be questions on this also. Okay. So that's about thermal expansion. So if you remember these formulas, there can be questions on this. There can be so many questions. Okay. Suppose they can say that there can be questions like, if the, like say you can write it here as delta L by L is equal to L0 into delta T, right? Delta L by L is equal to L0 into delta T, right? From this you can write out. Okay. So there can be a question, if you want to restrict the change in length, if you want to restrict the percentage expansion within 2%, what should be the temperature rise? Or what should be the, what can be the temperature? Like suppose you want to restrict the expansion to 2%, 2% increase, then
Substitute
what,
that and
what will
find.
be the maximum temperature rise permitted?
Yeah.
So those questions, so if you know this formula, with this you can do, they can twist the questions in n number of ways, okay. Sometimes percentage means this by del L by L,
Yeah.
okay. So knowing that percentage, you have to use this formula, okay. So I think, I think delta L by L0 is equal to, sorry, alpha, okay, alpha, and this is L0, right, L0, right.
Yeah.
So that, like this formula, you have to just twist it in different way, and then you can solve. Okay. But the governing equation, just you have to remember this. And there can be some questions on area and volume. If you know this relationship, you can easily find out. Okay. You take a picture, then we'll go through. So the unit of alpha is
Kelvin inverse.
Kelvin inverse. Okay. So for different, it's a property of matter. Okay. For different material, the coefficient of thermal expansion will be different, right?
Yeah.
So it also depends on temperature, but yeah. So for a particular, say at room temperature, this is coefficient of thermal expansion. Okay. So now we'll get into this. Specific heat. Okay. So what is specific heat? Yeah. Okay. So specific heat of a substance, we can write it as, let us say, S. Okay. So S. So normally we write it is like that. Heat supplied is equal to mass into specific heat into rising temperature. So amount of heat supplied goes to rise the temperature. So amount of heat supplied is equal to mass of the substance into specific heat into rising temperature.
Raise it by unit temperature.
So here we can write it as S is equal to Q by
M
into delta
T.
Okay. So otherwise the definition of specific heat is that, so because in the numerator you have heat. Okay. So you write amount of heat
Needed to change the mass.
Heat needed to raise
unit mass by unit temperature.
raise unit mass temperature by unit. Okay. So if both are unit, then that is called your specific heat. Okay. And then
Unit of specific heat.
So there is this is called specific heat, and there is something called specific heat capacity. Okay. So specific heat capacity. So if you multiply this S into mass, that is called specific heat capacity. Okay. So that is specific heat capacity. It will be nothing but Q by delta T. That's all.
Yeah.
That is called specific heat capacity. Okay. And there is something called the molar specific heat. Molar
N
specific.
into number of moles.
Molar specific heat means number of moles will be there in the denominator. Molar specific
Q by
heat.
N delta T.
Molar specific heat. Okay. So it is kind of Q by delta T by number of moles. Let us say N. Okay. So how you find number of moles? So number of moles is equal to your mass
by mole.
Mass divided by molecular mass. Molecular mass. Okay. So suppose you have let us say 28 gram of nitrogen. Okay. Or let's say nitrogen
28
has a molecular mass of 28, right? 28 gram, right?
yeah,
So
28 by 28. So
Mhm.
1
So
mole.
it becomes N becomes 28 by 28 is equal to 1. Okay.
28 grams of nitrogen
Huh.
has 1 mole
Huh.
of
Yeah.
nitrogen.
Yeah, number of moles. Suppose you have 56 grams of nitrogen. That means N is equal to 56 by 28. So it becomes 2
2
moles.
moles of
So
nitrogen.
in the denominator, 2
N
moles
is
will
2.
come. Okay. So that is about specific heat. Okay. And there is something else that is called the latent heat. Okay. Latent heat. Latent heat. Okay, so when you raise the temperature of water, okay, so let us say your water is at minus 10 degree. It is ice. So anything below 0 degree centigrade is ice. So your ice is at minus 10 degree centigrade. Now you keep supplying heat. The temperature will rise to 0 degree. Okay, so there will rise in temperature. Once it reaches 0 degree, there it will start melting.
Their change of state. will
Change of state. So the latent means what?
Hidden.
Hidden or invisible. Okay. So you cannot see any rise in temperature when the melting is happening or
But
vaporization
it
is
is
happening.
at that temperature that the change of state takes place.
Yeah. So the amount of heat required to convert unit mass of solid to liquid or liquid to vapor
gaseous.
is called latent heat of melting or latent heat of vaporization. Okay. So latent heat formula is something like L is equal to amount of heat per unit mass. So this amount of heat required to convert the substance from one state to the another state. Okay. So it is something like this. So you have say del T. You have temperature rise here, and you have heat supplied here. Okay. If you have a curve like that, so how you will see how the curve is going to be. Okay, so it will be something like this. Okay, so it will be like this, like this. Okay. Then it will be like this. It will be like this, something like this. So let us say this is kind of, let us say this is kind of 0 degree, right? This is, you are heating water, so this is 0 degree, right? This is 0 degree centigrade, right?
Yeah.
Then here it has started boiling, so this is 100 degree centigrade. 100 degree centigrade. Okay. So let us say you have started at minus 10 degree centigrade. Okay. So when it is minus 10 degree centigrade, it is ice. Okay. So this is ice. Okay. Then at 0 degree centigrade, you don't see any rise in temperature. So what is happening? Here the melting of ice is taking place. Okay. Here melting of ice is taking place. Melting of ice taking place. So what happens actually when a solid gets converted into liquid? The molecular force between them decreases and they go away. So you know, in solid they are very close. In liquid they are, the molecular force is less, and in gas they become free.
Yeah.
So that energy is going to like melt the solid to liquid, and that's why there is no temperature rise. Whatever energy you are giving, it is making changing the state rather than increasing the temperature. That's why you are getting a straight line there.
Yeah.
Okay. So this is melting point. Then again the temperature will rise. Okay. And here the boiling happens. Okay. Boiling. Boil. Okay. So this is called. So first is latent heat of fusion. Second one is latent heat of vaporization. So this is ice here. Okay. Then this is water. Okay. And then this is the steam. Right. Right. So see, here also it is a boiled water. When it reaches 100 degree centigrade, that is called a boiled water. So you say that by boiled water you will not have a burn, but in the steam it will have a lot of heat in it, not the boiled water, right?
Yeah.
So now you understand what is specific heat and what is latent heat and all. Okay. So I think latent heat of water is something like 80 calorie per gram.
Gram.
So that value will be there. Then and there is a relationship between this calorie and
Joule.
joule. Okay. So that value you can find out. Okay. Okay. So with this background, let us try to solve one numerical on this. Okay. You take a picture of this. Okay. So the numerical is like this. When 0.15 kg of ice at 0 degree centigrade, so it is given as 0.15 kg of ice at 0 degree centigrade. Okay. So it is ice. 0.15 kg of ice at 0 degree centigrade is mixed with 0.30 kg of water at 50 degree plus 0.30 kg of water at
50 degree.
50 degree centigrade. Okay. Uh, the resulting temperature is 6.7 degree centigrade. Okay. So you have water in a container. So you have like say 0.3 kg means 300 gram of water, right? 300 gram of water at 50 degree centigrade. Okay.
Yeah.
And you have poured some ice into it. Okay, some ice you have poured. So this ice was like say 150 gram of ice you have poured, and which is at 0 degree centigrade, right? So and they have given, after you mix it, the resulting temperature is 6.7 degree centigrade. Resulting temperature is 6.7 degree centigrade, right? So they are asking calculate the latent heat of fusion of ice. Okay. So question, find latent heat of. So this is kind of an experiment to find the latent heat. In lab you do. Okay. Latent heat of fusion of ice. So you have an ice with 0.15 kg, but after mixing it with water, it is getting converted to water at 6.7 degree centigrade.
Yeah.
So from this, how you will find the latent heat of fusion of ice? Okay, because your ice, by mixing with the hot water, it got converted into water.
Yeah.
But the temperature of water has come down from 50 degree to
To
6.7 degree. Okay, so the heat that is being lost by water. So your water has remained water.
Yeah.
Okay, only ice has got converted to water.
Water temperature has changed.
So how much heat has been given up by water? Okay, so whatever heat you see, water has given away the heat and become cooler, and that heat is being used to melt the ice, right? So how much heat is given away by water? Okay, so heat given away by water. Okay, so it is mass into specific heat into delta T. Okay, so your mass is like say 0.3 kg. Okay, and on input is specific heat of water is 4186 joule per kg per Kelvin. Okay, so S water is given, specific heat is equal to 4186 joule per kg per Kelvin,
Kelvin.
right? So you have to be very careful. You have to convert everything to Kelvin. Okay. So it is so S and I have to multiply it by 4186. Okay. And Kelvin. So my 50 degree centigrade. So it becomes 50 plus 273 is my initial temperature, and 6.7 plus 273 is my final temperature, right? So this is actually 323 and this is like say 279.7.
Yeah.
Okay, so just if you see the difference, finally it will be becoming for 50 minus 6.7, right? Right?
Yeah.
Which is equal to 42.3, right? Or 43.3.
43.3.
So this is 43.3. Okay. So this much of heat is
I have to
given.
convert that so into Kelvin.
We have converted because but 273 will cancel out, right?
Okay.
That's why it is same.
Okay.
Right?
Okay.
So 43.3 if we multiply, then I find the heat given away is 54376.14. Okay. So this is 54376.14 joule. Heat unit is joule. Okay. So this much of heat is given away by the hot water. Okay. So this heat is used to melt the ice and then raise the temperature to 6.7. It was at 0 degree. So you are melting the ice. After melting, you are raising the temperature from 0 to 6.7, right?
Ice temperature from 0 to.
So this ice was at 0. Okay, so this was ice. So first you have to melt this ice from ice to like water at 0 degree. Okay.
That happens from the heat that is given by
That
water.
is, so this water is giving the heat. First it is melting the ice, then it is raising the temperature. Okay, so this, so heat given away. So Q given is going as, okay, that is mass of ice. Okay, is given going as mass of ice, m ice, okay, into the latent heat of ice, latent heat of fusion. Okay, I can write it as latent heat of fusion. Okay, LF. So this plus the same mass of ice, mass will anyway remain same. Okay, so mass of like that ice, it has become water. So that m into 0 to 6.7. So you have to multiply it by 6.7. Right? So so the final equation will be like say 54376.14 is equal to mass of ice. I know it's 0.15 kg, right?
Yeah.
0.15 kg into LF, which is our unknown that we have to find out. Okay, LF plus the same like
that we found out mass of water and 6 into 6.
So yeah, so again 0.15 into
6.7.
6.7. So this is your equation. This is your equation. So you have one equation with one unknown. So this LF is what you want to find out. So LF, if you solve it, you will find this LF to be 3.34 into 10 to the 5. So LF is equal to 3.34 into 10 to the 5
Joule kg inverse.
joule per kg.
Joule per kg.
Joule per kg. Okay, so your LF is equal to 3.34. So you if you convert into kilojoule, it will become 334 kilojoule per kg.
Latent heat unit is just joule per.
Joule per kg. So your latent heat of fusion you will find as 334 kilojoule per kg. So you need 334 kilojoule of heat to convert 1 kg of ice to water, right? So you are studying about the tonnage of a refrigerator. So if the tonnage is say 1 ton, that means it will convert. So that much of heat the refrigerator is about to take from the substances inside the refrigerator. So that means the amount of heat that refrigerator is about to take from inside the refrigerator is 1 ton. What does 1 ton means? Means 1000 kg of water can be converted to ice. That much of heat it is taking away.
Yeah.
That is the meaning of tonnage.
Yeah.
Okay, so here latent of heat of fusion is 334 kilojoule. Okay, that kilojoule you can convert into calorie by dividing by 4.18 or some value is there. So that is 80 kilocalorie. That's how you convert kilojoule to kilocalorie. You will check what is the value, what is the relationship between kilojoule to kilocalorie or joule to calorie. So maybe that is 4.18 or something. So it will become 80 or something. 80 kilocalorie per kg or 334 kilojoule per kg. Okay. So that is about the latent heat, and then we'll discuss about heat transfer and a few more numericals in the next session. Okay. Okay. Thank you.